Okay, thank you everyone for joining us today on this webinar. My name is Vikram and I work for GL Communications. I am joined on this webinar my two colleagues, Rob Bishevsky, our Director of Engineering, and John Phipps, our Senior Engineer. Um, the topic of today's webinar is testing solutions for satellite communications networks. So here we're all about testing satellite networks, and that's the focus of today's webinar. I think most of you are familiar with us, but in case you are not, we are GL Communications. We've been around for over 35 years. We are headquartered in Gaithersburg, Maryland, right outside of Washington, D.C. We have two divisions at our company. One is our consulting division, and one is our test and measurement products division. What we will be talking to you today is our test and measurement products division. We manufacture equipment that can test all different types of telecommunications networks. Satellite networks, wired networks, analog, TDM, Ethernet, IP, SONET, cellular networks, 2G, 3G, 4G, 5G, land mobile radio, and so forth. I kid you not, we have test solutions for all of these different types of networks. Our solutions can do a lot of different things on these networks. We can generate traffic, we can analyze traffic, we can store traffic, we can visualize traffic, we can do a lot of different types of analysis and emulation and storage type solutions over these networks. Today, though, what we want to talk specifically about is satellite communications testing. So there's a huge expansion and improvement in satellite communications networks these days. Every single day you hear on the news about more and more satellites being launched into outer space. Countries like the United States, China, countries in the European Union, and so forth are all putting up satellites in record numbers. This is because it's also become easier to launch these satellites on rockets, and there are more companies, private companies and public sector companies available that can launch these satellites. So now we have thousands upon thousands of satellites in outer space, many different companies and governments hosting these satellites, and it has led to an incredible improvement in connectivity and user experience. Now, who is using the satellite networks? Government agencies and contractors are using satellite communications networks for mission critical applications. Everything from, military, talking to your troops deployed on the ground or at sea. But you also have private sector companies and individuals as well, families and individuals who are using satellite networks for home internet. So a wide range of different use cases for satellite communications networks. Now, satellite networks have evolved dramatically, and they can now transmit everything, all different types of voice, video, and data traffic. So just like any other network, wired or wireless, satellite communications networks can transmit voice, video, and data services. As many of you know, the main advantage of satellite communications networks is that it's wireless, and therefore it can reach remote locations without the need for wired infrastructure. Mountains and deserts and ships at sea can all now communicate directly via satellite. So that's the main advantage of satellite networks. The disadvantage is that these networks are still low bandwidth networks. I know that there are now advertisements out there for gigabit internet access over satellite, and I know that the bandwidth is improving, But nonetheless, satellite networks really cannot compete with fiber optic networks, for example, in terms of bandwidth, nor can they compete in terms of latency. Latency meaning the signal has to be beamed out into outer space. The satellite has to process the information and beam it back down to Earth, and that will introduce latency of several milliseconds all the way up to seconds even of latency. Whereas fiber optic networks are more point-to-point, and they will have lower latency. Also, because satellite networks are wireless-based networks, they can experience all sorts of environmental degradations, interference, poor signal strength in bad weather, and so on and so forth. Also, in outer space, you have solar storms and effects from the solar wind and other types of adverse environmental conditions that can affect satellite communications technologies. So with that in mind, GL Communications is a testing company. We test networks, and satellite communications networks must be tested, rigorously tested for availability, for user experience, meaning voice quality, and fundamental packet metrics, such as throughput, packet loss, latency, jitter, and other types of metrics. So a lot of customers need to test satellite communications networks. They need to test them regularly, periodically. They need to do repetitive testing over and over again, or continuous monitoring. And so that is all a huge request for many companies when they come to us. Now, in addition to testing real-world satellite networks, a lot of companies need to emulate satellite networks. A lot of companies that develop applications that use satellite networks need to test if those applications work correctly over satellite networks. And they need to emulate a satellite network before going live and actually deploying it on a real satellite network. So if you're deploying an application that is streaming video or voice or whatever, you want to emulate a satellite network and then see how that application behaves in that emulated environment, and see what are the unexpected consequences of going over an emulated satellite network. So in this webinar today, we are going to discuss 3 different topics. We're going to talk first about emulating satellite networks. And then after we talk about emulating satellite networks, we're going to discuss traffic generation over real satellite networks, all different types of traffic generation. And then after that, we are going to focus on voice quality testing specifically over satellite networks. Probably the third bullet is probably our most requested use case, so we'll spend the majority of the time talking about that. So let's go ahead and get started. Again, okay, so the first topic is satellite network link emulation. When we talk about emulating satellite networks, we are specifically referring to the impairments that occur over a satellite network. So, like I mentioned before, satellites will experience low bandwidth, long latency. They will be noisy networks. They'll drop packets, introduce bit errors, jitter, packet reordering, packet duplication, and other types of impairments, just like any other network as well. So when we emulate a satellite network, we are going to do it with one of our cutting-edge products called the Packet Expert. And the Packet Expert will sit in line on your network. All of the traffic will pass through the Packet Expert and then back out and back through onto your network. The Packet Expert acts like a transparent link. So your network does not see it. It's like it's almost, think of it as a network tap. It's just passing traffic back and forth. However, it can it can very selectively impair the traffic as it passes through the device. As you'll see on the following slides, you can precisely control the bandwidth passing through the device. You can precisely control the latency, the packet loss, the jitter, bit errors, and so forth passing through the device. And because you have precise control over this, you can emulate a lot of different impairments that you would see over a satellite network. So if a real satellite network is introducing 0.1% packet loss, you can put 0.1% packet loss into this device and then see how your applications behave. How does packet loss impact user experience? How would it impact voice quality or video quality? How would it impact TCP throughput and so forth? You'd be surprised, but even a low amount of packet loss can dramatically impact TCP throughput, for instance. So like that, this is how the solution is deployed. So I hope this graphic makes sense. Instead of sending the traffic over the real satellite network, you will send it through our packet expert. So some of you are familiar with the packet expert, but in case you are not, it is it can be a rack mountable appliance, or we can provide a portable system as well. But the bottom line is that it has many wired Ethernet ports, and the traffic will pass through these Ethernet ports. We support fiber optic as well as electrical connections via RJ45. And we support 10, 100, 1000 meg connections, as well as 10 gig connections through the packet expert. The packet expert is controlled by a Windows PC, and a lot of times customers ask us to include the Windows PC in the chassis for an all-in-one solution, and we can do that. So in the back panel you see here on the right hand side, we actually place the controlling PC right here, and it's connected internally to the packet expert. This controlling computer is running Windows operating system. It's got its own HDMI and USB ports so that you can connect a monitor, a mouse, and a keyboard to it. It also has its own Ethernet port so you can remote into it. And the software that's running on the Windows PC directly controls the packet expert hardware. You'll see on the next slide some screenshots of the software. It is very easy to use and very easy to set parameters for how you want to impair the traffic. So this is an all-in-one solution. It's our rack-mountable solution. You can access it locally. You can access it remotely. So you can deploy it out in the field. You can deploy it at a ground station. You can deploy it at a central hub. You can deploy it at a network room and so forth. And you can remotely access it or locally access it to control the packet expert hardware. It's a 1U rack mountable enclosure. We can actually stick multiple packet experts into the 1U enclosure. We do also offer these optional TTL triggers. I won't talk about them too much, but if you have questions about them, we can certainly address those. Okay, so the packet expert software is very, very easy to use. Through a click of a button, you can reduce the bandwidth, for instance, through a click of a button, you can set all of the different parameters for controlling the traffic flow through the packet expert. So I will show you a series of screenshots here. The first screenshot is how you can reduce the bandwidth. You can reduce the bandwidth in both directions, of traffic or a single direction of traffic. So going from port 1 to port 2 or from port 2 to port 1, you can set the traffic rate to be whatever you want. You can reduce the traffic all the way down to 10 kilobits per second. So we can go anywhere from a maximum of 10 gigabits per second if you're on a 10 gig link, or we can go all the way down to 10 kilobits per second. And again, you can set it differently for different directions. So that's through this symmetrical and asymmetrical option here that you see. Okay, now for latency, the same exact concept. You can change the latency in either direction independently, or you can make them the same. The latency, we can go all the way down. You can introduce a maximum latency of 4 seconds, and you can introduce a minimum latency of 100 microseconds. If you completely turn off the application, then the application will not introduce any latency at all, or it'll introduce latency on the nanoscale. So it'll be negligible latency. But once you turn on this latency feature, you can go all the way from 100 microseconds to a maximum of 4 seconds. Now, delay in the real world over a satellite network will not be constant. Every single packet will experience a different delay value. So because of that, we can emulate different types of probability distributions. A uniform distribution would be like each packet would experience a delay of between a range of values with equal probability. A random exponential distribution, that's your normal distribution or a Gaussian distribution, centered centered at some value between the minimum and the maximum. So the majority of the packets will experience, let's say, 2 seconds of delay, but then there's a probability. So some of the packets will experience 2.1 seconds of delay. Some of the packets will experience 1.9 seconds of delay, and so forth. So it's all based on a probability distribution, which is the most realistic solution, which is the most realistic expectation for a satellite network or any network, to be quite honest. And again, the distribution in either direction can be set independently. Don't expect the traffic in one way to behave like traffic in the other direction. There's all sorts of asymmetries involved in satellite networks. So this is latency. Moving on, packet loss. Again, it's the same exact concept. Both directions are independent. You can go all the way down to 0.002% packet loss, and all the way up to 50% packet loss. The packet loss can be periodic. So if you say 50% packet loss, or let's just say like 10% packet loss, that packet loss can be periodic, meaning 1 out of every 10 packets are dropped, and it's very periodic. Every 10th packet will be dropped. However, in real networks, it's more random than that. So we also offer a random packet loss based again on probability distributions, but set to the desired rate that you set it at. So we can do packet loss in a variety of ways. You can also manually click to introduce a single packet being dropped. So if you just want to drop one packet whenever you wish, you can at runtime just click drop, and it'll drop that one packet. So sometimes customers just want to see they're looking for a very, very specific effect when just one packet is dropped, and they want to see if their application will detect it. So you can just, by the click of a button, click drop, and it'll drop one packet just like that. And and you can do it as many times as you wish. So again, packet loss is very customizable, um, and we can do it in a lot of different methods. We can reorder packets. If you send 5 packets from point A to point B, it's very likely that the second packet arrives before the first, or the third arrives before the second, or the fifth arrives before the third, or the fourth. So that's another example of jitter, where you have variable delay. And so reordering packets is another way to emulate jitter. Same principle as before. You can click a button to just introduce one reordering event, or you can have a steady stream of packets being reordered, something like 1 out of every 5 packets or something like that, 1 out of every 1,000 packets, and so forth. I'll go now a little bit faster since I think you get the point. We can also do packet duplication, and we can also do bit error insertion. So we can insert bit errors in selected packets. Bit errors meaning flip the bit. We'll flip the bit in the payload or flip the bit wherever you want it. Actually, you can determine what byte offset to flip the bit at. So bit error insertion is also easily doable. You can insert FCS errors, frame check sequence errors as well, to test how your network is handling frames with incorrect FCS errors. Typically, switches will simply drop frames with incorrect FCS checksums, but that is a configurable setting, and so you can test that by introducing FCS errors. Now, the application will return an enormous number of statistics for you in both directions. It'll tell you what how many frames have gone through, what's the average throughput, the minimum throughput, maximum throughput. It'll tell you how many packets it's dropped, how many packets have been reordered, how many packets have been duplicated, how many packets have bit errors, and so on and so forth. You'll get a whole wide range of metrics. You can export the data, save the data, and so forth. This is all in real time, so these numbers get updated in real time. And here again, I show you a lot more statistics on all of the traffic being transmitted through the device. You can see all sorts of different statistics: size of the frames, checksum errors, IPv4, IPv6, TCP packets, UDP packets, and so on and so forth. You get just an enormous amount of data about everything that you could want to know about the traffic going through the packet expert device. Here, I just show you a quick example of how we drop the throughput. So you see like this green line here. Periodically, we are dropping the throughput. We drop the throughput dramatically from 200 megabits per second all the way down to 20 megabits per second, and then back up again, and then drop it again, and then back up again. So this is just an example of throttling the throughput to whatever value we desire for however long we want to throttle the throughput. We could leave the throughput depressed for indefinitely, or we could periodically bring the throughput down and bring it back up. It's all easily doable. Now, one other important thing I want to mention: you can define different streams of traffic and impair them differently. So what do I mean when I say a stream of traffic? It could be different IP addresses, or different frame sizes, or different UDP ports, or TCP ports, or VLAN tags, or whatever different types of traffic. You can define that traffic and then impair it differently using this packet expert device. So here you see that maybe there's different types of traffic flowing across at different throughputs, and then we can impact each stream of traffic independently. This is important because maybe there's certain types of traffic you want to impair, but there's other types of traffic that you don't want to impair going through the device. So you have selective control with this application. Okay, so I know I'm talking really fast, but I want to move on and now talk about actually generating traffic. Previously we covered emulating satellite networks, but now let's talk about actually generating traffic over real satellite networks. So now we're going to be an endpoint device, and we are going to generate traffic over a real satellite network. Again, we do it with the Packet Expert 10GX, same hardware platform as before. And here we are at the endpoints. So the Packet Expert will be interfacing at a wired connection at a ground station. It's basically anywhere where a wired to wireless conversion can happen. So the Packet Expert connects at a wired interface at the ground station. It is then converted to wireless, beamed up to the satellite, beamed back down to a different ground station, and at that ground station you can have another Packet Expert deployed at that far end. That way you can do an end-to-end test across the satellite network. You can set different types of traffic, different traffic streams across the satellite network, get it at the far end, and then loop it back. So the Packet Expert at the far end will loop the traffic back and send it back over the satellite and back to the near end Packet Expert. By doing that, you can make a ton of different measurements. You can determine what is the round trip delay in the packets going across the satellite network. You can also determine the throughput, packet loss, and all the other metrics that I mentioned before. And so at the local end, you can make all the measurements. And at the far end, you can just deploy the Packet Expert and basically just forget about it. It'll act as a loopback, and you don't really need to manage it or anything. It's just in a perpetual loopback mode. And so you can get all the measurements at the local end. It's the same hardware platform, but just a different software license in order to generate the traffic over the satellite network. We can actually then generate up to 16 different streams of traffic simultaneously over the satellite network. So for a stream could be different IP addresses, MAC addresses, frame sizes, UDP ports, TCP ports, and so on and so forth. Remember that over a real satellite network, there will be different types of traffic flowing over the network, and there could be prioritization schemes in place over that satellite network. So the satellite network may prioritize certain traffic streams over other traffic streams, or that prioritization may happen at the ground station itself. So you can test those prioritization schemes by generating traffic with different protocol headers and seeing how what's the resulting throughput, the round trip delay, and so forth. So that's what the Packet Expert can do for you in terms of generating traffic over real satellite networks. Like I mentioned before, real satellite networks can handle voice, video, and data traffic. Typically, data is transmitted over TCP. Voice and video traffic is transmitted over UDP. So, and in general, any streaming service is transmitted over UDP. The Packet Expert can do both. It can transmit TCP and UDP traffic. We also have other applications and other software programs that can specifically transmit VoIP traffic, SIP and RTP type traffic over the network. So again, this goes back to testing different types of traffic streams. The Packet Expert and our other software programs can transmit different types of traffic over the satellite network. Now you can test how prioritization is done over the satellite network by putting in different protocol headers, usually at the IP address, sorry, at the IP protocol header level. So you can input a different class of service value for each stream, or you can input a different DSCP value for each stream. And then you can send out each stream over the satellite network, get the data back, and see, oh, okay, this stream of traffic had a different round trip delay than the other stream of traffic. So with each stream of traffic, you can really test to make sure that your satellite network is prioritizing the way you want it to prioritize. Remember, the satellite network is transmitting mission critical applications, and so mission critical applications may get priority over normal traffic flows. So maybe streaming services like voice and video will take priority over just simple web traffic, and so forth. So that is all, you can test all of that with the Packet Expert. I hope that's clear. So now what I want to do is I want to transition away from the Packet Expert and talk about another solution of ours that is specifically for voice testing over satellite networks. I'm joined by my colleague Rob Bashevsky. He will take over from here and talk specifically about voice testing over satellite networks using a different solution than the Packet Expert. He will be talking about our vMobile solution. This is, like I mentioned at the beginning of the broadcast, this is one of our most requested testing scenarios. Many companies who are doing satellite testing are interested in the user experience, the actual voice quality that they're going to get over the satellite network. So at this point, I will hand it over to Rob. And Rob, feel free to begin.
All right, thanks, Vikram. Yeah, so what Vikram was saying is he talked about testing the satellite network, testing the throughput of the satellite network, and also how to generate traffic over the satellite network. What this product is, it's actually simulating or becoming a headset to either a radio or a mobile device in order to generate traffic over the satellite network. So the device doesn't actually generate it doesn't actually connect to the satellite network, but it connects to devices that will connect to the network. So this device, the vMobile, it's a small handheld device. It's battery powered. It also has a USB-C for charging it, so you can put on a external battery pack on this as well if you're out in the field for a long period of time. It has GPS embedded within, so it's great for drive testing or walk testing or any type of mobile type of testing where you want to plot the results within Google Maps, for instance. It's got Wi-Fi embedded, so when you're out in the field, you can connect to a Wi-Fi hotspot or make your mobile phone a hotspot, and then that's used for you can control the vMobile through the Wi-Fi, or you can also send the results and all the recorded files and so forth back to a central system where they'll be analyzed. Controlling the vMobile, You can use the little screen. So it has a little screen with some buttons, so you can select the script and run that script, or stop the script, um, connect to the Wi-Fi network, things like that. So you can do that from the screen. You can also do it from the, as I mentioned, through the Wi-Fi connection. We have a console, web-based console to control the V-Mobile. We also have an app for both for Android and iOS in order to control the V-Mobile, and that can be controlled through the Wi-Fi connection or through a direct Bluetooth connection. So using Bluetooth, you can connect the phone or tablet or what have you right to the V-Mobile and then fully control it, configure it, perform the operations, run manual tests even. All that can be done through a Bluetooth connection to the V-Mobile. Now, the V-Mobile includes two different types of interfaces for the mobile devices. So it includes a single PTT interface, push to talk, so you can connect it to any radio. That includes 4-wire analog along with 2 wires for the PTT enable disable. So we can connect to a radio, disable PTT, or enable PTT, send audio, disable PTT, and then receive audio, all automatically. And we can write scripts to perform these operations fully automated. It also includes 2 Bluetooth interfaces to connect to 2 different Bluetooth phones. And here we become a headset to the mobile phone. A wireless headset to the mobile phone where we can control the phone, send commands to the phone to place a call, answer a call, disconnect a call, get some information from the phone, such as the single strength, battery level, things like that. So we can get information from the phone and bring it back to the V-Mobile. And then also send and receive audio for performing a bunch of different audio tests. And again, this can be done fully automated using the scripts within V-Mobile. So consider the V-Mobile more of a user experience to the mobile phone and mobile radio connections, communication connections. So, and this is specific for radio testing. So, we're going to connect to the radio. Now, the radios can be, we don't care how the radios are connected. They could be point-to-point radios, or they can go over a network. And in this case, they would go over a network through the satellite and come back down. So in that case, we would, again, connect to the radio as a headset, enable the PTT, send audio into the radio. That audio would go through the satellite and come back down. We record it at the other radio, and then we'd analyze the recorded audio for a bunch of different tests, such as voice quality. So we would use we can use the Polka algorithm, which is ITU-P863. If necessary, we can also use the PESC algorithm, which is ITU-P862. Now, the Polka has superseded the PESC algorithm quite some time ago, but there are still customers that want to maintain PESC. We can also use the PESC scores and do a conversion to DAQ. So that's also available within this solution. Now, not only can we get the voice quality scores, but we can also perform a bunch of other measurements using that recorded audio and provide a signal level gain, noise level gain, speech activity, frequency analysis, power analysis, audio dropout analysis. All that is available as part of the recorded file. And we can also do delay measurements, and I'll get into that in a few minutes. So again, we're on both sides of the call. We're sending audio, receiving audio, and then we're analyzing that audio. This can all be done fully automated using the scripts. and it can also be done manually within the vMobile. The other thing to note is that we have another product called our vQuad with a piece of hardware called WTA, and that's more of a lab instrument. And just to note that the vMobile can work with the vQuad as well. So if one end was vQuad and the other end was vMobile in the field, that works no problems. They can communicate to each other and make sure everything's in sync. So the vQuad has its biggest plus is that you can have 12 devices on a single system, 12 radios or 12 phones or any combination. So that's the biggest plus on that. But for any type of portability, the vMobile is much better. The other thing to see here is in the solution, all the results, as I mentioned, the vMobile has a Wi-Fi connection, so all the results go to a central system. And in that central system, you'll have your voice quality software for analyzing the file for Polka or PESC. You also have another piece of software called VAT, voice analysis tool, which performs all the other types of analytical measurements, such as the signal level, noise level, audio dropout, delay measurements. All that is done. And then the other thing at the central system is a database where all the results are being stored, and then you can access it through what we call our web viewer, which is a web browser, and the web viewer can filter the results, query the results, generate custom reports with line and bar graphs, and then also plot results directly on Google Maps if you're doing any type of drive or walk testing. So multiple vMobile and vQuad devices can connect to the same database, and then you can filter it based on test or location or whatever. You can filter it based on the device you use, whatever you want to do, so that you're only looking at your results from the big database. And this would be testing, performing the same thing, but testing on mobile phones. So again, we're connecting to the mobile phone, any carrier, any network. It doesn't matter to us if it's legacy, if it's the latest standard 5G, if it goes beyond 5G, it doesn't matter to us. Any device we can connect to. We're just a headset to the device. And we support narrowband and wideband. We'll soon support super wideband as well with this. For the analog side, we support narrowband, wideband, and super wideband audio. So in this case, we're connecting to the mobile phones through Bluetooth, and we're controlling the phone and then sending and receiving audio, and performing the same type of tests, such as the Polka analysis, and all the other metrics and the delay measurements. The other thing we can do with this, since we're going through a mobile network and we're generating a call, if you have to traverse an IVR, we can do that because we can send DTMF digits, as well as detect DTMF digits. We can send any frequency tone. We can also perform speech to text conversion. So if you're going through an IVR, for instance, we can record the audio and then traverse that to text, and then analyze if that's what we were expecting, if that's the right prompt we were expecting. So we do a lot of IVR testing as well with this solution. So now we'll talk a little bit about the delay measurements. So this solution supports one-way delay and round-trip delay. So one-way delay is very simple. You're going to send audio from the first vMobile. It's going to go through the device, or into the device, through the network, over the satellite, up and then back down into the far end device, and then back into the vMobile. and we're going to record the audio on the second V-Mobile. So we're sending and recording at the exact same time, so that we can then use a correlation algorithm to analyze the recorded audio against what was sent and provide a delay measurement which is accurate to less than a millisecond. In order to do this properly, we have GPS at both ends, so we're using the GPS clock to synchronize the two ends, so that we can start both ends at the same time. This works for radios, for mobile phones, doesn't matter. We can get very accurate delays. And as Vikram mentioned earlier, the delay over the satellite can be well over a second. I've seen them into the over 5 seconds, 7 seconds even, and that's not a problem for this. So we can calculate the delay, very high delays or very small delays. So this is round trip delay. Now round trip delay doesn't really work for radios since we're doing a push to talk. And you have to enable and disable. We do have a round trip delay support for radios using our V-Quad, using a different type of function. And it sort of has a protocol because so that one end is push to talk and the other end is actually getting the audio and then sending new audio back out, or a pulse. It's actually doing a pulse for the round trip on the radio. But for this solution, for the V-Mobile, the round trip would only work for the mobile phones. So what we're doing is the near end is sending audio, again, sending audio into the phone. The phone is sending that audio up to the satellite and back down, back into the far end V-Mobile. That V-Mobile is actually looping the audio back. So taking whatever it gets in and looping it back out, so that the audio goes back all the way to the near end V-Mobile, and then that V-Mobile is both sending and recording at the same time. Now, in certain cases, we'll actually delay the loop back audio from the far end to avoid any type of echo that might be within the network. So there may be an inherent delay at the far end, and then we just subtract that out at the near end. So in this case, the near end is going to send and record, and then we can again analyze and provide a round trip delay that is better than 1 millisecond. Also, in this case, you do not need the GPS. Since where the far end is, again, it's just in a loop back mode, and the near end can send and receive simultaneously using its own clock. So no GPS is needed, yeah, so this will provide the round trip delay. Now, the other thing to mention, and Vikram touched on this earlier, when you're performing, for instance, one-way delay, and you're performing it from device 1 to device 2, don't assume that you're going to have the same delay going from device 2 back to device 1. It's going to be 2 different delays. That's why a round trip delay is good. It'll show the full delay. So if you do a round trip delay from 1 to 2, you should get the same from 2 to 1, or roughly the same, depending, if you're doing it during the same call. But the one-way delays would be different. So it's a lot of times it's better just to do the one-way delay so you know what the delay is in each direction. So that's pretty much what the V-Mobile is, a portable solution to provide user experience from the mobile phones and mobile radios, and perform a variety of different audio tests. I hand it back to you, Vikram.
Okay, thank you, Rob. So that concludes our webinar. Thank you all so much for joining us on this webinar. And please feel free to contact us at any time. You can email us at info@gl.com. to discuss your testing scenarios. Also, please subscribe to our newsletter where we weekly put out new announcements and about our latest solutions and products. Thank you.